It is section 7.4, relative rates of growth and convergence. You may have noticed already that exponential functions such as e to the x and 2 to the x grow more rapidly than polynomials or logarithms as x approaches infinity. In the first part of the section, we'll compare growth rates of those functions precisely using mathematical terms. Let's see the definition. Assume that f and g are positive for x sufficiently large. If the ratio f over g approaches infinity as x approaches infinity, or equivalently g over f approaches 0, then we say that f grows faster than g as x approaches infinity. Or we can say, and g grows slower than f. If the ratio approaches to L, which is finite and positive, not 0 and not infinity, then we say f and g grow at the same rate as x approaches infinity. Okay, with this definition, let's try to solve the problems. Compare the growth rates of common functions as x approaches infinity. Okay. Now, we'll use the definition. In definition, here we have to check the ratio, the fraction. Okay. Here, and e to the x over x squared. And we want to try to get the limit. So the limit x approaches infinity. Okay. Here, bottom and top simultaneously approaches infinity, so that we can use L'Hopital's rule. Okay, that is same as here, the same limit, and derivative of e to the x is the same as the original one, and bottom becomes 2x. Again, here, top and bottom approach infinity. So again, we can use once more L'Hopital's rule. So let's same limit, and e to the x over 2. Now, bottom is a constant, and top approaches infinity, so that the value must be infinity. Okay, so we can conclude that e to the x is growing faster than x squared. Let's write down that one in this way. Okay. Now 2 to the x and 3 to the x and 2 to the x. Okay, the same way. We start with the fraction 3 to the x over 2 to the x. That is same as 3 over 2 to the x. 3 over 2 is larger than 1, and x approaches infinity, then the whole value will convert to infinity. That means here 3 to the x is growing faster than 2 to the x, right? Okay, now we'll compare logarithm x and x to the r. Okay, r can be positive, 0, or negative. Let's begin with here the case r negative. Then we know that x to the r is approaching to 0, so that here definitely now logarithm x will be is going to infinity, so that is growing faster than that one. So here logarithm x, in this case here, is now growing faster than x to the r. Quite easily we can say that. Secondly, if r equals 0, then x to the r is 1. So again, we can say now the same thing. Okay, thirdly now, and r is positive, then x to the r is increasing, approaching infinity as x approaches infinity. So that we have to measure the limit of the ratio x goes to infinity and logarithm x over x to the r. Top and bottom approach infinity, so that we can use L'Hopital's rule. Okay, same limit, and derivative of logarithm x is 1 over x, and x to the r, its derivative is r times x r minus 1. Okay, we try to get here, we multiply x bottom and top, then it becomes here 1 over r x to the r. R is positive and x approaches infinity, so that that one will approach 0. Okay, so that means that if we compare logarithm x and x to the r, then x to the r is growing faster than here logarithm x once r is positive. And even though very small r, and x to the r is growing faster. Okay, here, now again the same way. Okay, logarithm base a over x divided by logarithm base b of x. Okay, we can rewrite this one in this way. Natural logarithm of x over natural logarithm of a divided by natural logarithm of x over natural logarithm of b. Okay, so that is same as now natural logarithm of b over natural logarithm of a. Here we assume that a and b are larger than 1, so that as x approaches infinity, 2 are positive. The ratio is always same as this constant. Okay, let's say this is L. So we can say that logarithm ax and logarithm bx grow the same rate. Yeah, that is the case here. This one, they are growing at the same rate as x approaches infinity. Okay. Now, by using the definition, you can compare the growth rate. Now, in this example, even though this example is simple, we'll try to show that we may try to compare the growth rate by using an intermediate function, which is very familiar with. For example, for these two functions, we first compare and the first function n x, and again x n the second function. And if they grow at the same rate, then we can conclude that these two grow at the same rate. Okay? Okay, let's try to prove part A. Okay, same A. And here ratio, but limit x approaches infinity, and square root of x squared plus 5 divided by x. Okay, but this term is the same as if we divide by x top and bottom, then instead of radical, we have to divide by the terms by x squared. So the 1 plus 5 over x squared, and the bottom is 1. Okay, so as x approaches infinity, the value must be 1. That means that, and square root of x squared plus 5 and x grow at the same rate. Now, part B, again, same. Limit x approaches infinity. Now, we can write down x first, or this term first, it doesn't matter. So let's say x is on the top, and now that is 2 square root of x minus 1 squared. Okay, from here, the same limit and x, and we can expand the bottom. That is 4x. Now minus 4 square root of x and plus 1, right? And we can divide both top and bottom with x. Then we can reach at here, top is x and bottom is 4 minus 4 over square root of x and plus 1 over x. As x approaches infinity, the top, okay, must be 1, right? Okay, top must be 1. Okay, as x approaches infinity, here the value must be 1/4. That means that xn, 2 square root of x minus 1 squared, are growing at the same rate. So by using these two claims, we can conclude that these two functions grow at the same rate as x approaches infinity. Okay? Okay, this is the end of the part 1.